Hey everyone, it's Darshan Senthil, and in this video we shall be talking about the continuity of functions. This is an important concept in calculus and it will play a major role as we go through even to more advanced concepts like concavity and derivatives and stuff like that. Okay, so let's get started. So before we start determining the continuity of a function, let's go ahead and just talk about what it means for the function to be continuous. If a function is continuous, then basically you can draw it without lifting your pencil or your pen or whatever, honestly. So what this means is that, for example, if I had the function y equals x squared, then I could technically go on forever and ever and ever and keep drawing this without ever having to take my pencil off the piece of paper, right? Or in my case, the screen of my tablet, right? So that's basically what it means for the function to be continuous in simple terms. So if you're ever in doubt, just think about, can I draw it with my pencil? That's it, okay? Now, for the functions we've seen before, the reason we could just plug in the values was because we knew that it was continuous. So for example, we knew that x squared was continuous everywhere, meaning that there were no places where it had a break or a hole or anything. So therefore, we were just able to plug in the values and we'd evaluate. I should be specific here. When evaluating limits, was that we could just do it because we knew it was continuous. And you'll see the exact reasons for this in just a second, but this is the general idea for what this is. This will sort of explain why we've been able to do that without testing the left and the right hand limits. Okay, so let's move on then. So the rules of function continuity. First, let's define a function. So for a function f of x at a point A. Okay, let's call that point A. First thing, the limit as x approaches A of f of x must exist. Next, f of A must exist. And lastly, the limit as x approaches A of f of x must equal f of A. Okay, so these are the three postulates of function continuity, and again this explains why we were able to just plug in the value into the function to find the limit at that point. So again, just think about it. For all the continuous functions we've used, like x squared, 3x squared, x to the fourth, all those functions, the reason we could plug this in is because they're continuous. Now, which functions were the ones we could not plug that in for? Those were the functions that were not continuous. So for example, 1 over x or stuff like that, those are not continuous everywhere because you can't plug in 0, it's not continuous everywhere. So therefore, we were not able to plug in those right there. We were not able to plug the value in. However, for functions that are continuous for that point, we can go ahead and plug those in. We could go ahead and plug it in. Okay, so this is why. So you've seen it in action, and this is why we could do it without testing the left and right hand limits. Okay, so now let's just go ahead and see how each of these postulates proves that a function is continuous at a point. So let's draw a rough graph here. I'll use a different color for this. Let's go to green, or maybe red. Red is better contrast. Okay, so if the limit as f approaches A exists, what does that tell you about the function? Let's say A is over here. What does that tell you about the function to the left and the right of f of A? Well, it exists to the left and the right of A, right? So that at least immediately to the left and immediately to the right of A, it exists. So what happens beyond here and beyond here is none of our concern, but at least immediately to the left and the right, it exists. Okay. Now f of A must also exist. That means there is something that fills in the gap here. That's what that guarantees. Okay. Now limit of f of x as x approaches A equals f of A guarantees that A will be defined right between the two sides. Because often you will see cases where it's undefined here and it's defined like way up here, and that would not be continuous. This postulate here ensures that it's defined right there. So let's just recap. Determines that left and right exist. Okay, so this just determines that this confirms that the left and the right exists. This confirms that the point exists, so there's no hole. And this confirms that point connects the, I don't know how to word this, but completes the chain, I suppose. And is not like up here. Okay, so it's not up there, it's right there, and that makes us happy. Okay, so that's basically what each of these three postulates confirms. Okay, so these are the three rules upon which we shall be working our problems. Let's move on. Alright, ladies and gentlemen, let's go through our first example for determining the continuity of functions. Again, I should make the point that for these functions, the only time we really have to use these things is when we're talking about piecewise functions. Because for piecewise functions, because we have them all like stitched together in this weird way, where we often have to use these rules to determine if the function is going to be continuous at specific points. Okay, so you'll see what I mean by that in just a second. So let's look at our first example. Y equals, it's going to be 4x minus 6 if x is less than 2. It's going to be negative 7x plus 16 provided x is greater than or equal to 2. Okay, this is our problem. So let's just lay out a couple of things here. So what do we know about these two functions? So what do we know about them? Like if I gave you the function and I asked you, actually wait, let me just ask what we're looking for first. So we're going to find out, is f of x everywhere continuous? Okay, we're gonna find out if f of x is everywhere continuous. So if I gave you something like f of x equals 4x minus 6, like just that function, you would not need to go through all the processes, because you know right off the bat that linear functions are continuous everywhere. Therefore we kind of know that from just by looking at both of these functions that to the left and the right of x equals 2, the function is continuous. Okay, just by looking at these from the right, just looking at it from the bat, right off the bat, we know that it's going to be continuous to the left and the right of x equals 2. So let's just write that out. We know that f of x is continuous everywhere to the left and right of x equals 2. And how do we know this? Because the two functions are linear. Okay, so you may ask now, why do we need to go through this process at all? If we know both these are continuous, then we should just be able to say that it is continuous everywhere. But let me ask you this. So let's assume that this line is 4x minus 6, so that would be like, let's draw a little graph here, and let me give you a little representation of what could happen. So let's say the graph was something like this. Okay, let's say if we had a graph like this. Let's say we had a graph like this. Okay, now are both these functions, this is a piecewise function obviously, so are both these functions linear? Yes, they are. So they by themselves are continuous everywhere. However, because this is a piecewise function, there's this huge gap here, this huge discontinuity here, and therefore the limit would not exist here, and f of the limit would not exist here, so therefore it's not continuous. So this is the situation that we're trying to avoid here. Because it's a piecewise function, we don't know what's happening at that value. So that's our major point. So we must test at x equals 2 to ensure that nothing weird is happening there. So for example, because we switch functions on the piecewise there. Okay, so we must test that x equals 2 to ensure that nothing weird is happening there, because we switch functions there. So we switch functions here, and therefore we could have a gap like this. We could have something weird happening. So to make sure that that's not what's happening, we need to go ahead and just test for continuity at x equals 2. Okay, so to do that, we need to go ahead and lay out our postulates for determining function continuity. Okay, let's lay that out. Continuous if and only if the limit as x approaches 2 of f of x exists. That by itself would take care of any situation like this, because in this situation the limit would not exist. Okay, so therefore if this was true, it would bring us down to something like this. It would at least ensure that the limit that there's no jump discontinuity here or anything. It's just that this point may not exist, but the function is approaching the same thing from both sides. This would cover this. This would eliminate this situation. Now the next thing, f of 2 must exist. F of 2 exists. Okay, that would make sure that we have some point here, that this is not just a hole. And lastly, they must equal. This will ensure that f of 2 is right there and fills the gap and is not like somewhere up here. Okay, that's basically what that does. So now let's go ahead and evaluate the three of those. So first, let's go ahead and take the limit. The limit as x approaches 2 of f of x. So again, let's break this up. As we always do, we'll need to break this up into two parts. Again, because just as we did it with the example with piecewise functions in the previous video, we don't know for sure if the limit's going to exist. So we need to test both the left and the right. Okay. So here we're going to test the left. And the right. Okay, so let's do the right first. So if it's to the right, which of these functions would we use? Well, we use this one because x is greater than 2, which means it's going to be to the right of 2. Okay, so that would be the same thing as the limit. So x approaches 2 of negative 7x plus 16, which would be the same thing as negative 7, 2 plus 16 equals 2. Okay, now let's try this one from the left. So to the left would just be this one because it's less than 2. So this would be the limit. X approaches 2 4x minus 6, which is 4 2 minus 6, which is basically going to be 2. Now since the two of these equal each other, we can just say that the limit is 2. Okay, so that's one part covered. Now let's take it to step 2. F of 2. This is the same thing as, well, where we look for f of 2, we look here, because f of 2 is greater than or equal to 2 at 7x minus 16. So we basically take negative 7, 2 minus 16 plus 16. Sorry, I might have had a slip of the tongue there. This would equal, so also equal 2. And lastly, are they equal? Well, when I last checked, 2 equal 2. So yes, they are equal. So therefore, f of x is continuous everywhere.